A distant star's death might one day rewrite the rules of medicine. The vast emptiness of space is not separate from our world. It is directly shaping our future on Earth. We are on the verge of 30 incredible discoveries that could redefine life as we know it, from finding a second home for humanity to unlocking new forms of energy. We will journey to worlds with hidden oceans and unravel the mystery of a force tearing the cosmos apart. How many of these cosmic breakthroughs do you think will directly touch your life within the next 50 years? That distant star's death is a stark reminder of our own world's fragility, a fragility that makes our first discovery so profound. For centuries, we looked at the sky and saw only pinpricks of light, wondering if any other Earth circled those distant suns. Then we found them. Worlds like Kepler 186f and Proxima Centauri b are not just dots on a chart, they are revolutions in our understanding. Each one orbits within a region around its star known as the habitable zone, a place often called the Goldilocks zone. It is not too hot and not too cold, a narrow band of space where the temperature could allow for liquid water to pool on the surface. Think of it like finding the perfect spot by a campfire, close enough to feel the warmth but far enough away that you do not get burned. For life as we know it, water is the essential ingredient. Where there is liquid water, there is at least a chance for biology to take root. The discovery of these worlds does more than just expand a catalog, it fundamentally changes the question. We are no longer asking if there are other planets out there. We are now asking which of them might be home. The knowledge that rocky, Earth-sized planets exist in these comfortable orbits around other stars transforms our place in the cosmos. We are not necessarily alone on a solitary island. We may be living in a neighborhood teeming with possibilities, and the search for a second home for humanity has shifted from science fiction to a tangible, driving goal for science itself. The universe suddenly feels both vastly larger and strangely more intimate, and if a planet's location is the first clue, then its atmosphere could be the first message. That first message, however, is not written in words but in light. When a distant exoplanet passes in front of its star, a tiny fraction of that starlight filters through the planet's atmosphere. Scientists capture this faint signal using powerful telescopes like the James Webb, and within that light, hidden like a cosmic fingerprint, are the chemical signatures of the air itself. They are searching for biosignatures, specific combinations of gases that, on our own planet, are produced almost exclusively by living things. Oxygen, for instance, is a highly reactive gas that quickly binds with rocks and other elements. Its persistent presence in an atmosphere is a puzzle that, on Earth, is solved by the constant, planet-wide work of photosynthesis from plants and microbes. Finding oxygen and methane together is an even stronger clue because these gases react with each other and would normally cancel each other out. Their simultaneous existence suggests something or someone is continuously replenishing them. Think of it like walking into a room and seeing a steaming cup of coffee on a table. You did not see anyone make it, but the evidence points strongly to a recent living presence. That is the power of a biosignature. It is a proxy, a ghostly signal of activity we cannot yet see. A confirmed detection would do more than just answer an ancient question. It would shatter our biological solitude. We would have to accept that life is not a singular miracle on Earth, but a common, perhaps even inevitable, process in the universe. This knowledge would ripple through every field, from biology and chemistry to philosophy and religion, forcing us to reconsider what it means to be a living being in a cosmos that is suddenly and undeniably alive. But finding the ghost of life on a distant world is one thing, finding its physical remains is another. Our own solar system holds a promise of such a discovery, written not in light but in stone. The red planet Mars is no longer just a bright dot in the night sky. It is a world whose dusty surface has been read like a history book by our robotic explorers. Rovers like Curiosity and Perseverance have driven through dry, cracked landscapes that were once the beds of raging rivers. Orbiting spacecraft have mapped vast deltas and shorelines, the unmistakable scars of a world that was once blue and wet. The evidence is not just geological, it is chemical. Instruments have detected water ice locked away at the poles and hidden in the soil, and they have found minerals like clays and sulfates that only form in the presence of persistent liquid water. This is not a story of a brief, catastrophic flood, but of a planet that enjoyed lakes and oceans for billions of years. Think of it like finding the fossilized imprint of a seashell on the peak of a mountain, a silent testament to a world turned completely upside down. This discovery does two profound things. First, it ignites the hunt for past or even present microbial life. Where there was water for so long, life could have taken hold. Every scoop of Martian soil is now a potential treasure chest, possibly containing the fossils of ancient Martians. Second, and just as critical for our own future, that water ice is not just a scientific curiosity. It is a barrel of rocket fuel and a canteen for thirsty astronauts just waiting to be tapped. It is the single most important resource for establishing a permanent human presence off our world. The water of ancient Mars could very well become the lifeblood of humanity's first extraterrestrial home. And if water is the foundation for life and exploration, then the source of that energy is the engine that makes it all possible. That same Martian water could one day fuel a voyage to meet a visitor from another star. In 2017, our solar system received its first known tourist. Hurtling past the sun at blistering speeds, it came from the void between stars and was gone just as quickly. Astronomers named it Oumuamua, a Hawaiian word meaning scout. This was no ordinary comet or asteroid. Its shape alone defied explanation, a bizarre, elongated object tumbling end over end through the darkness, potentially 10 times longer than it was wide. Think of a cosmic cigar or a pancake silently sailing through the void. Its strange trajectory presented an even deeper puzzle. After it slingshotted around the sun, it sped up slightly as if pushed by an unseen force. Comets do this when their ices heat up and vent gas, creating a natural jet engine. But Oumuamua showed no visible coma, no tail of gas and dust. It was a dark, silent, and accelerating mystery. So what was it? The most grounded theory suggests it is a fragment of a Pluto-like world from another solar system, a shard of solid nitrogen ice chipped away in some ancient collision. As it neared our sun, the nitrogen would have vaporized, providing the thrust without creating a visible dust cloud. Another idea posits it is a cosmic dust bunny, an incredibly porous and lightweight aggregate born from the swirling disk of material around a young star. Then there are the more speculative possibilities. Its unusual shape and acceleration prompted some scientists to ask if it could be something artificial, like a light sail from an advanced civilization, a piece of forgotten technology adrift between the stars. While this remains a fringe hypothesis, its very discussion highlights how Oumuamua challenges our categories. It does not fit neatly into our solar system's filing cabinet of space rocks. This solitary scout is a messenger, and its message is that the building blocks of planets out there are far more diverse and strange than we ever assumed. The stuff of other solar systems is not just like our own. It can be weirder, more varied, and it is already passing through our neighborhood. The discovery of Oumuamua opens a new chapter in astronomy, one where the galaxy is not just a collection of distant lights, but a place of constant, tangible exchange. We are no longer just looking out at the stars. We are waiting for the next piece of another world to arrive on our cosmic doorstep. The silent passage of Oumuamua was a whisper from a distant shore, but some cosmic events are not whispers, they are screams that shake the very fabric of reality. In 2015, a ripple passed through our planet, a vibration so minuscule it stretched and squeezed a 4-kilometer-long laser beam by a distance 1,000 times smaller than the nucleus of an atom. This was the first direct detection of a gravitational wave, a confirmation of a prediction Albert Einstein made 100 years earlier. His theory of general relativity proposed that massive objects warp the space and time around them, like a bowling ball placed on a stretched rubber sheet. When two incredibly dense objects, like black holes or neutron stars, spiral toward each other in a final cosmic dance, they do not just orbit, they churn the spacetime around them, sending out waves of distortion that travel at the speed of light. Think of the universe not as a static stage, but as a vast, invisible ocean. Most of the time, the surface is calm. But when two whales collide beneath the waves, they send out ripples that travel across the entire sea. We are now, for the first time, able to feel those ripples. This discovery did not just prove Einstein right, it handed us an entirely new sense. Before this, we studied the cosmos almost entirely through light, from radio waves to gamma rays. Now we can listen to it, we can hear the universe. The chirp of two black holes merging a billion light-years away is a sound that was there all along, waiting for our technology to become sensitive enough to hear it. This new sense reveals a hidden, violent side of the cosmos, a realm of colossal collisions and catastrophic births that were completely invisible to our telescopes. It is as if we have been watching a silent movie of the universe for centuries, and someone has just turned on the sound, revealing a soundtrack of unimaginable power and violence. With this new ear to the cosmos, we are beginning to map the population of black holes, understand the death throes of stars, and probe the fundamental nature of gravity itself. Each new ripple is a story, a chapter in a cosmic history we are only just beginning to read. That soundtrack of cosmic violence is followed by a discovery of profound stillness and possibility. Just 40 light-years from Earth, a star named TRAPPIST-1 burns with a faint, cherry-red glow. It is an ultra-cool dwarf, a star so small and dim you could fit it between the Sun and Mercury's orbit. Yet this quiet star is the center of a stunning cosmic family, a system of 7 known worlds, each one roughly the size of our own. Think of it as a miniature solar system, a perfectly scaled model where all the planets are huddled close to their parent star. The entire system would fit comfortably within the orbit of Mercury in our own solar system. This proximity creates an extraordinary situation. From the surface of one TRAPPIST world, the other 6 would appear in the sky not as distant points of light, but as moons, some larger than our own, their features potentially visible to the naked eye. You could stand on a world and see multiple neighboring planets hanging there in a perpetual celestial dance. The true marvel, however, lies in the delicate balancing act of their orbits. These 7 worlds are locked in a gravitational harmony known as orbital resonance. Their years are precise mathematical ratios of one another, like a perfectly timed cosmic clockwork. This stability is crucial because it allows at least 3 of these Earth-sized planets to orbit within the star's habitable zone. The energy they receive from their faint red sun could be just right for liquid water to exist on their surfaces. A single solar system with not just 1 but 3 potential havens for life. This discovery shatters our previous assumptions about planetary systems. We once wondered if finding one Earth twin was a long shot. Now we have evidence that a single star can host a collection of them. The implications for the abundance of life are staggering. If such compact, life-friendly systems are common around the most numerous type of star in our galaxy, then the number of worlds with the right conditions for biology could be far greater than we ever dreamed. For future explorers, this system presents an ultimate destination. A single journey to the TRAPPIST-1 system would not offer one, but multiple new worlds to study, each with its own unique environment and history. It is a celestial archipelago, a chain of islands in the vast ocean of space, waiting for the day we learn to sail the stars. And as we look at these tightly packed worlds, we must also consider the forces that keep them in such perfect order, a delicate dance choreographed by gravity. The same gravity that orchestrates the dance of distant worlds also squeezes and pulls at a small, icy moon in our own backyard with astonishing results. Far beyond the orbit of Mars, in the deep cold of the Saturnian system, the Cassini spacecraft witnessed something that should not happen on a dead world. Saturn's moon, Enceladus, a gleaming ball of ice barely 300 miles across, was actively erupting. Immense geysers of water vapor and ice crystals were shooting hundreds of miles into space from fractures in its south pole, a clear sign of a vast, liquid ocean hidden beneath its frozen crust. This alone was a monumental discovery, but Cassini did more than just take pictures. It flew directly through those plumes. The data it sent back was even more stunning. Mixed in with the water were complex organic molecules, the heavy, carbon-rich building blocks essential for life as we know it. This was not just a whiff of simple chemicals, it was the signature of a sophisticated chemical kitchen operating in the dark. Think of Enceladus not as a frozen statue, but as a cosmic pressure cooker. Scientists believe the moon's core is warm, heated by the relentless gravitational squeezing from Saturn. This heat source likely powers Hydra, thermal vents on the ocean floor where superheated, mineral-rich water spews into the icy darkness. On Earth, such vents are vibrant oases, thriving with life that draws energy not from the sun, but from the chemistry of the vents themselves. The discovery on Enceladus suggests its hidden sea has all the key ingredients: liquid water, a source of chemical energy, and the complex organic Lego blocks needed to build something alive. This tiny, brilliant moon has instantly become one of the most promising places to search for life beyond Earth. It forces us to reconsider what a habitable world looks like. A planet does not need to be in a star's Goldilocks zone. Life could be thriving in the sunless oceans of icy moons, warmed from within by the gravitational embrace of a giant planet. The plumes of Enceladus are a free sample, delivering the secrets of its subsurface ocean directly to any passing spacecraft. A future mission could fly through these jets and analyze them for the ultimate prize, not just the building blocks of life, but life itself. Finding even a single microbe in that dark water would prove that the spark of life is not a rare fluke confined to Earth, but a common fire that can ignite wherever the right conditions persist. The story of life's origins on our own planet may be written not in our ancient rocks, but in the distant, erupting ice of a moon orbiting Saturn. The serene clockwork of orbital resonances and the hidden oceans of icy moons suggest a universe of delicate balances, but this harmony is an illusion on the grandest scale. A discovery at the close of the 20th century revealed a far more unsettling reality, one that dictates the ultimate fate of everything. For decades, astronomers assumed the expansion of the universe, born from the Big Bang, was gradually slowing down over time, pulled back by the collective gravity of all the matter in the cosmos. It was a logical expectation, like tossing a ball into the air and waiting for it to fall back to Earth. To test this, two independent teams set out to measure the slowing by observing incredibly distant stellar explosions known as Type 1, a supernova. These explosions are what scientists call standard candles. They have a known, predictable brightness. By seeing how much dimmer they appeared from Earth, astronomers could calculate their exact distance. They could also measure how fast they were moving away from us by the stretching of their light, a phenomenon called redshift. The results were not just surprising, they were shocking. The data from these faraway beacons showed that the universe is not slowing down at all. It is expanding faster today than it was billions of years ago. It is as if you tossed that ball into the air, and instead of falling back, it shot upward into the sky, accelerating as it went. This was a discovery so profound it earned the teams the Nobel Prize in 2011. Something was overpowering the pull of gravity, actively pushing the cosmos apart. That something was given a name: dark energy. This is not a minor force. Current measurements suggest dark energy makes up about 68% of the entire universe. It is the dominant component of reality, and we have almost no idea what it is. The leading theory suggests it is a property of space itself. Empty space is not nothing according to quantum physics. It seethes with temporary particles popping in and out of existence. This vacuum energy could generate a repulsive force that causes space to expand. The problem is, when physicists calculate how strong this vacuum energy should be, the theoretical value is off by a factor of 10 to the power of 120. That is a 1 followed by 120 zeros, arguably the worst prediction in the entire history of science. This discrepancy means our understanding of physics is fundamentally incomplete. Dark energy is not just a mystery, it is a direct challenge to our core theories. Its existence reshapes our cosmic destiny. If this acceleration continues unchecked, the universe faces a cold, lonely end known as the Big Freeze, where galaxies fly apart so rapidly that the sky beyond our local group will one day go completely dark, leaving future astronomers with no evidence that other galaxies ever existed. The force that governs the fate of the cosmos remains almost entirely unknown to us, a humbling reminder that the greatest discoveries are often the ones that reveal the vastness of our ignorance. While dark energy dictates a cold fate for the cosmos, a recent discovery right next door has ignited a firestorm of possibility. The scorching surface of Venus is a vision of hell, with temperatures hot enough to melt lead and a crushing atmosphere of carbon dioxide. For decades, it was written off as a sterile, dead world. Then, in 2020, astronomers announced a baffling signal from its upper atmosphere, the spectral fingerprint of a molecule called phosphine. On Earth, phosphine is a gas that is notoriously difficult to produce through ordinary geological or chemical processes. It is primarily associated with anaerobic life, microbes that thrive in environments without oxygen, like swamps and the guts of animals. Finding it in the temperate cloud decks of Venus was like detecting the smell of fresh bread coming from a blast furnace, a sign of something that simply should not be there according to our current understanding of the planet's chemistry. Scientists have scrambled to find a non-biological explanation, perhaps a strange, unknown type of volcanic activity or a novel atmospheric reaction. But so far, no abiotic process has been able to fully account for the amount of phosphine detected. This leaves one extraordinary possibility afloat, literally. High in the Venusian sky, about 30 to 40 miles above the surface, the temperature and pressure are surprisingly Earth-like. It is a strange, suspended oasis in an otherwise lethal environment. Could hardy, airborne microorganisms be living there, floating in the droplets of the planet's perpetual clouds, feeding on trace chemicals and producing this enigmatic gas? The idea forces us to tear up our old checklist for habitability. A world does not need a benign surface or a protective magnetic field. Life, it seems, could be an opportunistic tenant, surviving in the most unexpected of niches. The clouds of Venus are now a prime target for new missions, probes that could fly through them, sampling the air directly, searching not for fossils but for living cells. A confirmed discovery would be monumental, proving that life is not a rare miracle, but a stubborn, tenacious force that can take root even on our closest, most hostile planetary neighbor. That same dark energy pushing the cosmos apart governs the most extreme objects within it, objects whose very existence was once considered a mathematical fantasy. For generations, black holes were the ultimate unseen monsters, predicted by theory but forever hidden behind the impenetrable cloak of the event horizon. Then, in April 2019, a shadow appeared on the world's front pages. It was a hazy, fiery ring of light surrounding a central darkness, the first direct image of a black hole's silhouette at the heart of a distant galaxy called Messier 87. This was not an artist's impression, it was a photograph. Capturing it required an effort of almost unimaginable scale, the creation of a virtual telescope as large as the Earth itself. The Event Horizon Telescope collaboration synchronized the time on 8 radio observatories across the globe, from the high deserts of Chile to the peaks of Hawaii and the frigid landscape of the South Pole. By combining their data, they achieved a resolution sharp enough to read a newspaper in New York from a sidewalk cafe in Paris. What they saw was the shadow of the supermassive black hole, a beast weighing 6.5 billion times more than our Sun. The ring of light is not the black hole itself, but the photon sphere, the point of no return for light. Superheated gas and dust spiraling inward at near light speed in an accretion disk are bent by the black hole's immense gravity into this brilliant, lopsided halo. The darkness at its heart is the event horizon's shadow, a void from which no information can ever escape. This single image does more than just confirm these cosmic predators exist. It puts our fundamental laws of physics to the ultimate test. The size and shape of that shadow match the predictions of Einstein's general relativity with stunning precision, proving his equations hold firm even in the most violent gravitational arena imaginable. We are no longer just inferring black holes from the frantic orbits of stars around an invisible point. We are staring directly into their abyss. This transforms them from theoretical phantoms into tangible, physical objects we can observe and measure. The gateway to the most extreme environment in the universe is now open, and we are just beginning to peer through. The shadow of a black hole reveals the universe's extremes, but another kind of shadow holds the secrets to our own beginnings. While we peer into the abyss, a small spacecraft was performing a delicate ballet with a cosmic time capsule. The OSIRIS-REx mission did not just visit an asteroid, it touched a relic. Asteroid Bennu is a dark, rubble-pile world, a collection of rocks and dust that has remained largely unchanged for over 4.5 billion years. It is a pristine fossil from the dawn of our solar system. In 2020, the spacecraft descended toward this ancient terrain, not with a harsh landing, but with a gentle 5-second kiss. It extended a robotic arm that puffed a burst of nitrogen gas to stir up the surface material, successfully capturing a handful of the asteroid's primordial regolith. Think of it not as a rock, but as a sealed recipe book from the time before the planets were fully formed. This sample, now safely returned to Earth, is more than just dust. It is a direct line back to our own origin story. Scientists are now analyzing these grains for the presence of water-bearing minerals and complex organic molecules like amino acids, which are the fundamental building blocks of proteins. The question is profound. Did the raw ingredients for life, the very same ones that eventually sparked biology on Earth, hitch a ride on asteroids like Bennu? We may be holding the original Lego blocks from which our entire world and ourselves were assembled. Yet this mission has a second, equally urgent purpose. Bennu is classified as a potentially hazardous object with a small but real chance of impacting Earth in the late 22nd century. The close-up study revealed a surprising truth. Its surface is not solid rock, but a loose collection of particles behaving almost like a fluid. This knowledge is a game-changer for planetary defense. If we ever need to deflect such an object, we cannot treat it as a single, solid bullet. We will be pushing a floating pile of sand. A kinetic impactor might just sink in, while a nuclear device could simply blow it apart into a more diffuse, but still dangerous, cloud of debris. The sample from Bennu provides critical data on the asteroid's density, cohesion, and composition, informing the design of future deflection missions. This single journey has given us two priceless gifts: the key to understanding our past and the blueprint for protecting our future. Those ancient whispers from asteroids are now being met by a flood of light from the edge of time itself. The James Webb Space Telescope has opened its golden eye, and the universe is revealing itself in ways we never thought possible. Its first images were not just pictures, they were portals. When you gaze at the deep field image of galaxy cluster SMACS 0723, you are not just seeing a collection of distant suns, You are looking back over 13 billion years to a time when the first galaxies were being forged in the cosmic dawn. The faint red smudges in that image are not stars, they are infant cities of stars, seen as they were just a few 100 million years after the Big Bang. This is a view so deep it is like finding the baby pictures of our own Milky Way. But Webb is more than just the most powerful time machine ever built, it is a celestial chemist. It specializes in a technique called spectroscopy. When a distant exoplanet passes in front of its star, starlight filters through its atmosphere. Webb captures that light and splits it into a rainbow, a spectrum. Within that spectrum are dark lines like a cosmic barcode. Each line corresponds to a specific molecule in that alien air. Webb's immense sensitivity allows it to read these barcodes from atmospheres thousands of light years away with a precision we have never had before. It has already detected the clear signature of water vapor, along with hints of clouds and haze, in the atmosphere of a gas giant planet called WASP 96b. The next step is to train this power on smaller, rocky worlds in habitable zones, searching for those telltale combinations of gases like oxygen and methane that shout the presence of life. The telescope's early data is already challenging our stories. Some of those first galaxies appear brighter, more massive, and more structured than our models predicted for such an early epoch. It seems the universe might have gotten its act together faster than we thought, assembling mature galaxies in a cosmic blink of an eye. This could force a rewrite of the entire timeline of cosmic evolution, a fundamental rethinking of how everything we see came to be. With every new observation, the James Webb Space Telescope is not just adding new chapters to the story of the universe, it is forcing us to reconsider the very first page. Beyond the orbit of Neptune, in the frigid depths of our solar system, lies a realm of perpetual twilight. This is the Kuiper Belt, a vast donut of icy worlds left over from the construction of the planets. And in this distant frontier, the New Horizons spacecraft, after its historic flyby of Pluto, raced toward a tiny, enigmatic object named Arrokoth. What it found was not just another space rock, it was a fossil preserved in cosmic ice. Arrokoth is a contact binary, a shape that looks like two lumpy red pancakes gently stuck together. It is a pristine relic, untouched by the heat of the sun or the violent collisions that melted and reformed the inner planets. For over 4 billion years, it has floated in this deep freeze, its composition and form virtually unchanged since the very beginning. Think of it as a celestial time capsule, sealed at the dawn of our solar system and only now being opened. This strange, two-lobed structure is a critical clue to a long-standing mystery. How did the dust and gas of the early solar nebula first clump together to form the building blocks of planets? One leading theory, called pebble accretion, suggests that tiny grains of ice and rock slowly stuck together, building larger and larger objects. Arrokoth's gentle, bi-lobed shape strongly supports this idea. It appears to be the result of two separate objects that formed side by side in the same cosmic neighborhood, orbiting each other in a slow dance until their mutual gravity pulled them together in a merger so gentle it was little more than a cosmic kiss. There are no impact craters or compression fractures at their neck, just a seamless union. This tells us that the earliest stages of planet formation were not a chaotic, violent demolition derby, but a far more delicate and orderly process. The deep red color of Arrokoth's surface is another piece of the puzzle, caused by complex organic molecules called tholins. These are the same compounds that likely rained down on the early Earth, delivering the probiotic ingredients that may have eventually led to life. By studying this distant, frozen world, we are not just learning how planets are built, we are uncovering the delivery mechanism for the very chemistry that made us possible. Arrokoth is a direct snapshot of our own origin, a blueprint from a time before the Earth even existed, revealing that the grand architecture of our solar system began with the softest of connections in the coldest of places. That same cosmic blueprint from Arakoth is written in the gentlest of whispers, but the universe also speaks in sudden, deafening shouts. Without warning, a point in the sky explodes with energy. In a single millisecond, less time than it takes to blink, it releases more power than our sun will emit in 80 years. Then, just as suddenly, it is gone. This is a fast radio burst, or FRB. These cosmic flashes are one of the most perplexing mysteries in modern astronomy. They arrive from galaxies billions of light-years away, and for years they were solitary events, impossible to predict and even harder to trace. The first question was the most basic: what natural process could possibly be this violent and this brief? One leading suspect is a type of stellar corpse known as a magnetar. Imagine the core of a giant star collapsed into a city-sized ball, but with a magnetic field so intense it could erase a credit card from half the distance to the moon. A starquake on the surface of such an object, a sudden cracking of its crust, could theoretically unleash a titanic blast of radio waves in a fraction of a second, a scream of magnetic energy echoing across the cosmos. Then the plot thickened. Astronomers began detecting repeating FRBs. The same source would flare up again and again, sometimes in a frantic, unpredictable pattern. This ruled out one-time cataclysms like two neutron stars colliding. Whatever creates these bursts is not destroyed in the process, it lives to blast another day. The repeating nature inevitably sparked a more speculative, yet fascinating idea. Could these be artificial? Might they be the leakage from unimaginably powerful transmitters, or the thrust from light sails on interstellar ships built by an advanced civilization? While this remains a fringe and highly unlikely explanation, scientists take it seriously enough to study the signals for any sign of encoded pattern or structure that nature could not produce. But the true value of FRBs may not lie in their exotic origins, but in what they pass through on their way to us. These brief signals travel for billions of years through the sparse gas and dust that floats between galaxies. This diffuse material is notoriously difficult to see, yet it is thought to contain about half of the ordinary matter in the universe, the missing atoms that our inventories of stars and galaxies could not account for. As an FRBs radio waves journey through this fog, different frequencies are slowed down by slightly different amounts. By measuring this dispersion, scientists can effectively use the burst as a cosmic probe, weighing the invisible stuff that lies between the galaxies. Each FRB is like a single, brilliant flash of lightning in a foggy valley, illuminating the landscape for just an instant and allowing us to map the contours of the unseen. By counting these flashes and analyzing their twists and turns, we are not just solving a mystery of cosmic fireworks, we are taking a census of the universe's hidden backbone, 1 millisecond burst at a time. The faint scent of a swamp has no business on Mars, yet our robotic rovers keep detecting it. Traces of methane gas appear and vanish in the thin Martian air, a tantalizing and deeply frustrating puzzle. On Earth, the vast majority of methane is a byproduct of life, belched by cows and produced by microbes in wetlands and landfills. It is a classic biosignature. Finding it on Mars is like catching a fleeting, familiar scent on a wind that has blown across a dead world. The Curiosity rover has been our nose on the ground, sniffing the air inside Gale Crater. Its data reveals a bizarre pattern. Background levels of methane are incredibly low, almost zero. But then, without warning, sharp, mysterious spikes occur, where the methane concentration suddenly increases by a factor of 10 before fading away just as quickly. These are not constant leaks, they are sudden, localized puffs. So where are they coming from? The scientific debate is fierce, pitting biology against geology. One camp points to the possibility of subterranean microbes, Martian organisms that could be living in aquifers deep below the frozen surface, protected from the harsh radiation and producing methane as a waste product. These sporadic belches could then seep up through cracks in the ground, explaining the transient spikes the rover detects. The other, more conservative explanation involves geology. Certain rocks can produce methane through non-living chemical reactions. A mineral called olivine, common on Mars, can react with water and carbon dioxide in a process called serpentinization, releasing methane as a byproduct. It is possible that ancient reservoirs of methane, trapped in ice-like structures called clathrates, are occasionally ruptured by small Mars quarks or seasonal warming, releasing their stored gas in sudden bursts. Think of it like a dormant soda can, shaken and then suddenly opened. The problem is, our current data cannot yet distinguish between the two scenarios. Is Mars giving us a faint chemical hello from long-dead geology, or a subtle biological whisper from living tenants just beneath our feet? This mystery is so profound that it has directly shaped the design of the next generation of rovers. The Rosalind Franklin rover, part of the ExoMars mission, will carry a drill capable of reaching several feet down, far below the surface layer sterilized by radiation, to search for those very same organic molecules and perhaps finally provide an answer. The resolution of this mystery will define our understanding of Mars. If the source is geological, it still reveals a more complex, chemically active world than we knew. But if it is biological, it means we are not alone and that life in its simplest form is next door. Our galaxy is not drifting aimlessly through the void. We are caught in a vast, silent river flowing toward an unseen destination. For decades, astronomers have known that the Milky Way, along with our entire local group of galaxies, is racing at a staggering 2 million kilometers per hour toward a specific point in the cosmos, a region of space hidden behind the thickest part of our own galaxy's central bulge. This mysterious gravitational anchor is known as the Great Attractor. It is a colossal anomaly, a focal point of gravity so immense it is capable of tugging on tens of thousands of galaxies, orchestrating the motion of our entire galactic neighborhood. The problem was we could not see it. Our view was completely blocked by a dense curtain of stars, gas, and dust in the Milky Way's own galactic plane, a zone of avoidance that rendered our optical telescopes useless. It was like trying to identify a distant mountain range while standing in a deep, fog-filled valley. To pierce this cosmic veil, astronomers had to turn to a different kind of vision, using radio and X-ray telescopes that can see through the obscuring dust. What they began to uncover was not a single monstrous object, but something even more grand. The Great Attractor appears to be the heart of the Laniakea supercluster, a filamentary structure of galaxies that is 500 million light-years across and contains the mass of 100 quadrillion suns. Our own Milky Way is not even a major city in this cosmic metropolis. We are a small suburb on the outskirts, feeling the gentle but persistent pull of the bustling downtown core. This downtown is a massive concentration of galaxy clusters, with the Norma cluster at its very center, acting as the primary gravitational engine. Yet even this vast supercluster may not be the full story. There are hints that something even larger, perhaps an immense confluence of superclusters, lies beyond the Great Attractor, pulling on the puller itself. This discovery fundamentally changes our cosmic address. We are not just in the Milky Way or the local group or even the Virgo supercluster. We are part of Laniakea, a single, flowing structure defined by gravity's relentless current. Our journey toward the Great Attractor is a humbling reminder that even on the scale of galaxies, we are all subject to forces vaster than we can easily see, drawn toward a center we are only just beginning to map. Europa's frozen shell hides a secret so vast it dwarfs all the oceans of Earth combined. This gleaming moon of Jupiter, etched with a web of cracks and ridges, is not a solid ball of ice. It is a global ice cap floating atop a subsurface sea of liquid saltwater so deep it may hold more than twice the water found on our own planet. The evidence comes from the subtle wobble of Europa as it orbits Jupiter. The giant planet's immense gravity flexes and squeezes the Moon, a process that generates immense internal heat, enough to keep a global ocean from freezing solid despite the deep cold of space. This makes Europa a world of two extremes, a bitterly cold, radiation-blasted surface and a dark, warm, watery abyss below. Then, the Hubble Space Telescope saw something fleeting, immense plumes of water vapor erupting over 100 miles high from fractures in the southern ice. These are not constant fountains, but sporadic geysers, much like those on Enceladus, offering a free sample of the hidden ocean to any passing spacecraft. Think of it as a message in a bottle shot into space from an alien sea. This combination of a global ocean and accessible plumes catapults Europa to the top of the list in the search for life. The upcoming Europa Clipper mission is designed to be our translator for that message. It will not land, but will perform dozens of close flybys, skimming through those plumes with its sensitive instruments, analyzing the chemistry of the ejected water. It will search for complex organic molecules and even attempt to determine if the ocean floor has hydrothermal vents, those same kind of energetic oases that support entire ecosystems on Earth's seafloor. Could something be swimming in that perpetual darkness, sustained by chemical energy welling up from below? We may soon have an answer. The quest is no longer just to find water, but to see if that water is alive. A single positive signal from Europa's abyss would transform our understanding of biology, proving that life can thrive completely cut off from the sun in the lightless depths of an alien ocean. A cosmic shout pierced the quiet of an Ohio summer evening, a signal so powerful it made an astronomer scrawl 3 letters of stunned amazement on a printout. On August 15, 1977, the Big Ear Radio Telescope, a sprawling metal array scanning the sky for signs of intelligent life, recorded a burst of radio waves that defied all natural explanation. For 72 glorious seconds, the signal flooded the receiver. It was a strong, narrowband transmission, focused on a specific frequency that is naturally quiet in the universe, a frequency that many scientists believe is a logical channel for interstellar communication. It came from the direction of the constellation Sagittarius, and then, just as suddenly as it arrived, it vanished, never to be heard again. The astronomer who discovered the data, Jerry Amon, circled the alphanumeric code on the readout and wrote one word beside it: wow. That single word gave the signal its name, and the mystery has endured for nearly 5 decades. The search for a natural explanation has come up empty. It was not a passing satellite or a reflection from space junk. It did not match the signature of a known astronomical object like a quasar or a pulsar. The signal's intensity rose and fell in a perfect curve, exactly as you would expect if it were a stationary beacon being scanned by the Earth's rotation, a perfect match for an artificial transmission from a fixed point in space. So what was it? The possibilities range from the mundane to the extraordinary. Could it have been a secret military transmission or a brief, never-repeated glitch in the telescope's own electronics? Or was it, as the most tantalizing theory suggests, a genuine message from an extraterrestrial intelligence, a cosmic hello that we simply were not listening for long enough to hear again? The WOW signal's legacy is not an answer but a lesson. It reminds us that our search for cosmic companions is conducted in a sea of profound silence, punctuated by fleeting, ambiguous events. It is a ghost in the machine, a single, brilliant data point that proves how difficult this search truly is. A real signal would be persistent and repeatable, something we could verify. The WOW signal remains a beautiful, haunting outlier, a siren's call from the void that continues to challenge our assumptions and fuel our determination to keep listening. The haunting silence that followed the WOW signal stands in stark contrast to a whisper we have learned to hear from every direction at once. This whisper is the cosmic microwave background, a faint, cold glow that permeates all of space. It is the oldest light in the universe, the cooled and stretched remnant of the fireball of the Big Bang. When the universe was just 380,000 years old, it had cooled enough for the first atoms to form, allowing light to travel freely for the first time. That initial flash of light has been traveling ever since, stretched by the expanding cosmos into the microwave part of the spectrum. Today, it appears as a uniform bath of radiation with a temperature of just 2.7 degrees above absolute zero. If your eyes could see microwaves, the entire sky, day and night, would glow with this primordial energy. But this baby picture of the cosmos holds its deepest secrets not in its uniformity, but in its tiny imperfections. Space-based observatories like Planck have mapped this background with exquisite precision, revealing that it is not perfectly smooth. It is mottled with tiny temperature fluctuations, warmer and cooler spots that differ by only a few millionths of a degree. These minute ripples are the cosmic seeds of destiny. They represent regions of the early universe that were ever so slightly denser than their surroundings. Over billions of years, gravity acted on these density variations, pulling more and more matter toward them. The slightly denser spots grew into the first stars, the first galaxies, and the vast cosmic web of clusters and filaments we see today. Every grand structure in the universe, from a swirling spiral galaxy to the supercluster we call home, began as a tiny whisper in the static of the cosmic microwave background. By analyzing the precise patterns of these ripples, scientists have been able to assemble a standard recipe for the entire cosmos. The data tells us that ordinary matter, the stuff of stars, planets, and us, makes up a mere 5% of the universe. Dark matter, the invisible gravitational scaffolding, accounts for about 27%, and the remaining 68% is the mysterious dark energy driving the cosmic acceleration. This single ancient afterglow has given us our most complete inventory of reality, a blueprint that traces a direct line from the universe's first moments to the rich tapestry of galaxies we observe now. We are literally seeing the origin of all structure, the faint imprint that would one day grow into everything we know. That faint cosmic afterglow tells the story of our universe's gentle birth, but some cosmic events are anything but gentle. Sometimes a star makes a fatal mistake. It drifts too close to the immense gravity well of a supermassive black hole lurking at the center of its galaxy. For the star, there is a point of no return, a boundary called the tidal radius. Once it crosses this line, the force of gravity on the side of the star facing the black hole is catastrophically stronger than the force on the far side. This difference, the tidal force, stretches the star horizontally while compressing it vertically. The star is not simply swallowed whole, it is shredded. It undergoes spaghettification, pulled into a long, thin strand of stellar plasma in a process as violent as it is beautiful. This cosmic demolition, known as a tidal disruption event, unleashes a firestorm. The stellar debris does not vanish into the black hole immediately. It forms a frenzied, swirling accretion disk, a whirlpool of superheated gas and dust. As this material rubs against itself under unimaginable friction and pressure, it heats up to millions of degrees, blazing with light across the electromagnetic spectrum. For a few brief months, this single event can outshine every star in its host galaxy combined. Think of it as a cosmic bonfire where the black hole uses the star itself as fuel, creating a temporary beacon that we can see from billions of light years away. For astronomers, this is not just a spectacle, it is a unique laboratory. The brilliant flash of light is a probe, illuminating the immediate environment of a black hole that would otherwise be invisible. By watching how the light from the disruption event brightens and fades, scientists can measure the mass and spin of the black hole itself. They can study how matter behaves in the most extreme gravitational fields possible, testing the limits of Einstein's theories. Each tidal disruption event is a fleeting, natural experiment, offering a front-row seat to physics that we could never hope to replicate on Earth. These stellar deaths give us a direct window into the feeding habits of the universe's most enigmatic predators. While black holes shred stars in distant galaxies, we have sent our own probe to confront the star that gives us life. The Parker Solar Probe is a mission of audacious extremes, a spacecraft built to dive into the million-degree atmosphere of the Sun itself. Its destination is the corona, that beautiful, wispy halo of plasma visible during a total solar eclipse. This outer atmosphere is a profound mystery. It is hundreds of times hotter than the visible surface of the Sun below it, a violation of intuitive physics, like a flame leaping up from a block of ice. To solve this, we had to go there. The probe's journey is a feat of celestial engineering, using Venus as a gravitational brake to walk its orbit ever closer to the solar inferno. It is shielded by a revolutionary heat-resistant carbon composite shell, a 4.5-inch thick protector that keeps its instruments at room temperature while the front end faces temperatures hot enough to melt iron. In 2021, it officially became the first human-made object to touch the Sun, repeatedly flying through the corona to sample the star's atmosphere and the solar wind at their source. The solar wind is a constant supersonic flow of charged particles that streams from the Sun, flooding the entire solar system. Before Parker, we did not know how this wind was born or how it accelerated to such incredible speeds. The probe's direct measurements have been revelatory. It discovered that the Sun's magnetic field near the surface is much more dynamic and switchback-like than models predicted. Think of these switchbacks as sudden, S-shaped kinks in the magnetic field, whipping past the spacecraft like cosmic cracks of a whip. These phenomena appear to be a key mechanism for dumping energy into the corona, heating it and helping to launch and accelerate the solar wind. Understanding this process is not just an academic exercise, it is vital for our survival on Earth. The solar wind carries space weather, massive eruptions of particles and magnetic fields that can slam into our planet's magnetic shield. A powerful enough solar storm can induce massive electrical currents in the ground, overloading power grids and causing continent-wide blackouts. It can fry satellite electronics, crippling global communications, GPS, and weather monitoring. By learning how the solar wind is born, we move from being passive observers of space weather to active forecasters. The data from Parker is helping us build better models to predict these solar outbursts, giving power companies and satellite operators crucial days of warning to shut down vulnerable systems and protect the technological backbone of modern civilization. This mission transforms our relationship with our star from one of distant awe to one of intimate understanding, revealing the forces that create the very space we live in. Our solar system's outer darkness is far from empty, but the paths of the objects out there are telling a strange story. Far beyond Neptune, in the cold expanse of the Kuiper Belt, a cluster of small, icy worlds share a peculiar orbital trait. Their elongated paths around the Sun are mysteriously clustered, as if an unseen hand has gently herded them into a similar orientation. The gravitational pull of the known planets cannot account for this strange alignment. The most compelling explanation proposed by astronomers at Caltech is the gravitational influence of a massive, undiscovered world. This hypothetical planet 9 is thought to be a super-Earth, a world up to 10 times the mass of our own, tracing a vastly distant and elongated orbit that takes between 10,000 and 20,000 years to complete a single journey around the Sun. Think of it like watching a school of fish all suddenly change direction at once. You know there must be a larger, unseen predator lurking just out of sight, guiding their movements. The hunt for this ghost planet is one of the great modern astronomical quests. Telescopes like Subaru on Mauna Kea are methodically scanning the predicted swath of sky where it might be hiding, searching for a faint, slow-moving pinprick of reflected sunlight against the backdrop of fixed stars. Finding it would be a monumental achievement, but it would also force a dramatic rewrite of our solar system's history. How did a planet that large end up so far away? It may have been flung outward in the solar system's violent youth, a primordial giant exiled to the frozen fringe by a gravitational tug of war with Jupiter or Saturn. Its discovery would prove that our cosmic backyard is not yet fully mapped, and that a true world of significant size has been waiting in the shadows all along, a silent member of our sun's family finally stepping into the light. The silent, steady ticking of a cosmic clock is one of the universe's most useful gifts. When a massive star dies in a supernova, its core can collapse into an object of almost unimaginable density, a neutron star. Some of these stellar corpses begin to spin, and as they spin, they beam radiation from their magnetic poles. If these beams sweep across Earth like a lighthouse, we call the object a pulsar. Their regularity is staggering, with some pulsars spinning hundreds of times per second and ticking with a precision that rivals our most advanced atomic clocks. This incredible consistency makes them powerful tools for testing the very fabric of reality. When two pulsars orbit each other, they create a perfect laboratory for gravity. As they spiral inward, they lose energy by emitting gravitational waves, and the rate of their orbital decay matches the predictions of Einstein's general relativity with near-perfect accuracy. It is a direct, ongoing confirmation of a theory conceived a century ago, but their utility extends beyond pure science. Picture a future starship venturing into the dark between solar systems. The ship's navigator would not rely on a single star for guidance. Instead, she would use a network of known pulsars, each with its own unique pulse frequency, creating a celestial GPS for the galaxy. By comparing the arrival times of pulses from multiple pulsars, her ship could triangulate its position anywhere in the Milky Way with astonishing accuracy. This pulsar navigation system is not just science fiction, it is a concept already being studied for future deep space probes, and the predictable nature of these signals raises another profound possibility. A technologically advanced civilization might intentionally modify a pulsar's natural beam, perhaps by placing a structure in its path to create a patterned signal, a deliberate message etched onto the most reliable carrier wave in the cosmos. A pulsar could be transformed from a natural phenomenon into a galactic billboard, broadcasting its presence to anyone who knows how to read the subtle changes in its timeless rhythm. These spinning remnants of dead stars are more than just cosmic curiosities. They are potential lighthouses, timepieces, and signposts, guiding us through both the laws of physics and the vast, empty ocean of space. A silent, cosmic heart beats at the center of our galaxy, a monster hidden behind curtains of dust and stars. For decades, its presence was a shadow we could only infer, felt through the frantic orbits of stars trapped in its gravitational grip. Then, in 2022, we pulled back the veil. The Event Horizon Telescope collaboration delivered the first image of Sagittarius, a star, the supermassive black hole anchoring the Milky Way. That fiery, donut-shaped ring, though fuzzier than its counterpart in Messier 87, confirms a 4 million solar mass giant resides in our own backyard. This is not a distant abstraction, it is the dynamic center of our celestial home. But the black hole itself is only part of the story. The true drama unfolds in the space surrounding it, a cosmic ballet of stars and gas clouds moving at unimaginable speeds. One star, known as S2, whips around Sagittarius, a star in a 16-year orbit, accelerating to nearly 3% of the speed of light as it makes its closest approach. Picture a comet on a cosmic scale, streaking through a region of space where the gravity is so intense that its starlight is stretched and redshifted, a direct validation of Einstein's predictions. These stellar trajectories are not just a spectacle, they are the most precise probes we have for testing the laws of physics in an extreme environment. Astronomers watch these orbits with bated breath, looking for any tiny deviation, any wobble that might hint at a hidden population of smaller black holes, or even more exotic, reveal a crack in our understanding of gravity itself. Meanwhile, strange puffball objects orbit nearby, looking like gas clouds but moving with the purpose of stars. These G objects could be the shredded remains of stars whose outer layers were stripped away in a close encounter, their dense cores still holding together, cloaked in a veil of dust. Each close pass, each stellar scream, teaches us more about how black holes feed, grow, and shape their galactic environment. The chaotic dance at our galactic center is a natural laboratory of unparalleled ferocity, a place where the fundamental rules of the universe are written in the paths of captive suns. The dust of Mars holds more than just the story of ancient water. It contains the very ingredients that could have once stirred with life. While exploring the slopes of Mount Sharp, NASA, a Curiosity rover drilled into a rock and uncovered a surprising chemical signature, the element boron. This was not a random find. The rover discovered it concentrated within mineral veins, the fossilized plumbing of a long-vanished groundwater system. On Earth, boron is often found in places where water has evaporated, like dried-out lake beds and hot springs, environments that are often teeming with microbial life. But its role goes far beyond being a simple marker of wet conditions. Boron has a special relationship with one of the most important molecules for life, RNA. Ribonucleic acid, or RNA, is a fragile, chain-like molecule that many scientists believe was the first genetic material, the original architect of life before DNA took over. The problem is, building RNA's long, stable backbone is a tricky chemical process, especially in water. The sugars that form the backbone are notoriously unstable and tend to break down before they can form a chain. Boron comes to the rescue. It acts like a chemical clamp, binding to these fragile sugars and stabilizing them long enough to link together into the long strands necessary for RNA to form. Think of boron as a microscopic set of training wheels, allowing the first shaky structures of life to assemble without immediately falling apart. Finding boron on Mars does not mean we have found life, but it dramatically improves the odds that Mars was once capable of building it. It tells us that the ancient lakes and groundwater of Gale Crater were not only wet, but also chemically sophisticated, containing the right mix of elements to support the prebiotic chemistry that leads to biology. This discovery transforms Mars from a world that was merely habitable to one that was potentially proactive, a world that was not just waiting for life to arrive, but was actively brewing the components needed to spark it into existence. The presence of boron is a quiet but powerful clue, suggesting that the red planet was once a chemist's workshop, mixing the very recipes from which life could emerge. That same cosmic blueprint, written in the faint whisper of the microwave background, is now at the heart of a growing crisis in cosmology. We have two very different ways of measuring how fast the universe is expanding, a value known as the Hubble constant. One method uses the cosmic microwave background, that ancient afterglow from the infant universe. By meticulously mapping its tiny ripples, we can project forward, calculating what the expansion rate should be today based on our standard model of cosmology. It is like calculating how fast a teenager will be able to run as an adult based on their precise genetic blueprint. The other method looks at the modern universe, using pulsating stars called Cepheid variables and cataclysmic supernova in nearby galaxies. These objects are what astronomers call standard candles. Their known intrinsic brightness allows us to measure their distance with high precision. By observing how fast these galaxies are rushing away from us, we get a direct present-day measurement of the expansion. This is like using a radar gun to clock the sprinter's speed today. The problem is, these two numbers do not match. The local, modern measurement consistently gives a faster expansion rate than the prediction from the early universe. This discrepancy is not a small, negligible error. It is a significant and stubborn gap that has survived years of re-examination and improved data, a conflict now known as the Hubble tension. At first, scientists suspected an unnoticed error, a miscalibration in one of the cosmic yardsticks. But as observations have become more precise, the tension has only tightened. This is not merely a statistical fluke, it is a genuine crisis. It suggests that something fundamental is missing from our picture of the cosmos. Perhaps dark energy, the force driving the acceleration, is not constant as we have assumed. Maybe it is evolving, growing stronger over time. Or perhaps there is an entirely new type of particle or field, a relic from the universe's first moments that we have not yet accounted for, subtly altering the expansion history. Another, more unsettling possibility is that our standard model of cosmology, the very foundation of modern astronomy, is flawed in some deep way. The implications are staggering because the ultimate fate of everything, the final chapter of the universe, hinges on the precise nature of this expansion. A faster expansion rate points toward a colder, lonelier, and more rapid dissolution of the cosmic web. The Hubble tension is more than a scientific disagreement. It is a crack in the foundation of our understanding, and through that crack, we might just glimpse a new kind of physics waiting to be discovered. That crack in our cosmic model, the Hubble tension, forces us to look back to the very beginning, to the first fraction of a second after the Big Bang. The leading theory for that primordial moment is cosmic inflation, a concept so radical it redefines the meaning of fast. The theory proposes that the universe, in its first sliver of existence, underwent a staggering growth spurt, expanding exponentially from a subatomic speck to something the size of a grapefruit in less than a trillionth of a second. This was not the steady, stately expansion we see today. It was a violent, inflationary surge that stretched the very fabric of spacetime itself. This incredible process solved several major puzzles in one elegant sweep. It explains why the universe appears so uniform in all directions, why the cosmic microwave background is so smooth. Regions of space that should never have been in contact with each other, according to the standard Big Bang model, were once neighbors stretched apart by inflation to create the vast, even cosmos we observe. But inflation did not create perfect smoothness. It was a quantum process, and that means it had tiny, inherent fluctuations. On the smallest scales, energy fields were jittering, and as the universe inflated at a dizzying rate, those microscopic quantum jitters were stretched to astronomical sizes. Think of blowing up a balloon with a faint, microscopic pattern printed on the rubber. As the balloon expands, that tiny pattern becomes a large, visible design across its entire surface. In the same way, inflation took the universe's quantum fuzz and stretched it into the grand, cosmic-scale density variations we see imprinted in the cosmic microwave background. Those slight overdensities, the warm spots in that ancient afterglow, are the very seeds from which all structure grew, the gravitational wells that would eventually pull in matter to form galaxies, stars, and planets. Without inflation's initial push, the universe might have remained a formless, homogeneous soup. We owe our very existence to that first, violent heartbeat of expansion. The search for definitive proof of inflation is one of the most important quests in cosmology. The most promising clue lies in a specific type of polarization in the cosmic microwave background, a twisted pattern in the light known as B modes. This signature would be the smoking gun, the fossil imprint of primordial gravitational waves generated during the inflationary frenzy. These are not the waves from colliding black holes we detect today, but the first ripples in spacetime itself, echoes of the universe's birth cry. Detecting them would be like listening to the first vibration of the cosmos. While tentative signals have been claimed, a confirmed detection remains elusive, driving the development of ever more sensitive telescopes both on the ground and in space. Confirming inflation would be the final, triumphant piece of the Big Bang puzzle, completing our story of cosmic genesis from a singular, unimaginable beginning to the rich and structured universe we call home. 66 million years ago, a day like any other ended with a flash of light brighter than the sun. A mountain-sized asteroid, perhaps 6 miles across, slammed into the shallow seas of what is now the Yucatan Peninsula in Mexico. The impact created the Chicxulub crater, a scar over 100 miles wide, and unleashed an energy equivalent to billions of atomic bombs. The immediate effects were apocalyptic, with superheated shockwaves, mega tsunamis, and a rain of molten rock spreading across the globe. But the real killer was what followed. The impact vaporized carbonate rock, releasing trillions of tons of sulfur and carbon dioxide into the atmosphere. Soot from global wildfires filled the skies, blotting out the sun for years. Earth plunged into a long, dark winter. Photosynthesis ground to a halt, collapsing the food web from the bottom up. The reign of the dinosaurs, along with 75% of all plant and animal species, was over. We know this story not from guesswork, but from a geological detective story. A thin layer of clay found in rock formations all around the world marks this exact moment in time. This layer is abnormally rich in the element iridium, which is rare on Earth's surface but common in asteroids. It is the cosmic fingerprint of the impactor, the silent witness to a bad day on a planetary scale. This discovery does more than explain the past, it frames our future. The same celestial mechanics that delivered that asteroid 66 million years ago continues to operate today. Studying the Chicxulub event is not just about ancient history, it is a stark warning and a practical guide. It tells us what happens when a large object hits, and more importantly, it fuels our efforts to make sure it never happens again. By mapping near-Earth objects and developing missions like DART, which successfully nudged a small asteroid, we are moving from being passive inhabitants of a cosmic shooting gallery to active guardians of our planet. The same space rocks that once ended a world may one day provide the knowledge that saves our own. A star named KSE 8462852 began to misbehave, and it captured the attention of the entire world. Found by the Kepler Space Telescope and nicknamed Tabby's star after its lead investigator Tabitha Boyajian, this seemingly ordinary point of light displayed a pattern of dimming unlike anything astronomers had ever seen. Stars can dip in brightness when a planet transits or passes in front of them, creating a predictable, repeating, and gentle fade. But Tabby's star did not follow the rules. It plunged into darkness by enormous amounts, up to 22%, in chaotic, asymmetrical, and completely unpredictable dips. The dimming was not clean and crisp, it was jagged and messy, as if something enormous and irregular was drifting in front of the star, blocking its light in a frantic, stuttering pattern. The strangeness was so profound that one of the most compelling, if speculative, explanations emerged. Could this be evidence of an alien megastructure? The idea was based on a concept from physicist Freeman Dyson, who proposed that a sufficiently advanced civilization would eventually need to capture nearly all the energy output of its home star. They might construct a vast swarm of orbiting solar collectors, a Dyson sphere, encircling the star and converting its immense power into usable energy. From our distant vantage point, such a structure, only partially completed, would block starlight in exactly the kind of bizarre, non-repeating way that Tabby's star exhibited. For a moment, it felt like we might be staring at the ultimate cosmic engineering project, but science thrives on ruling out the mundane before embracing the extraordinary. Further observations, particularly from the Hubble Space Telescope, revealed a crucial clue. The star was dimming more dramatically in ultraviolet light than in infrared light. This was a telltale signature. Any solid object, whether a planet or a giant alien machine, would block all wavelengths of light equally. Only something composed of tiny, diffuse particles like dust would scatter the shorter blue and ultraviolet wavelengths more effectively, letting the longer, redder infrared light pass through more easily. The verdict was in. The culprit was not a solid megastructure, but a colossal, swirling cloud of fine dust. The leading theory now suggests a catastrophic event, perhaps a collision between planets or the violent breakup of a moon, created an enormous debris field orbiting the star. This cloud, containing trillions of tiny particles, is what periodically obscures our view, creating the wild and unpredictable dimming. While this explanation dashes the dream of finding a Dyson sphere, it opens a window into a different kind of drama. We are witnessing the chaotic aftermath of planetary destruction, a stark reminder that the process of building solar systems is not always neat and orderly. It can be violent, messy, and full of cosmic wreckage. Tabby's star teaches us that the universe is capable of producing natural phenomena so strange they border on science fiction, challenging our categories and forcing us to look deeper. The most profound discoveries are not always the ones we hope for, but the ones that reveal the true, chaotic, and wondrous diversity of creation. Our planet's safety net extends far beyond its own magnetic field, stretching to the very edges of the sun's influence. This is the heliosphere, a colossal protective bubble carved out by the solar wind. For billions of years, this magnetic cocoon has enveloped our entire solar system, acting as a primary shield against a relentless, invisible storm. Outside our local sanctuary, the galaxy is flooded with cosmic radiation, high-energy atomic nuclei that scream across interstellar space at nearly the speed of light. These particles are the shrapnel from long-dead stars, and without a barrier, they would constantly bombard our world, making the surface a far more hostile place for delicate biological molecules. The heliosphere deflects the vast majority of this dangerous galactic radiation, creating a relatively calm harbor in a chaotic cosmic sea. Think of it as our solar system's weatherproof hull, keeping out the worst of the interstellar gale and allowing the stable, gentle conditions that life on Earth required to take root and evolve. We are only now beginning to understand the true shape and nature of this vital boundary, thanks to two incredible missions. The twin Voyager probes, launched in the 1970s, have become our first interstellar scouts. Voyager 1 officially pierced the heliosphere's outer layer in 2012, followed by Voyager 2 in 2018. As they crossed this final frontier, their instruments recorded a dramatic drop in solar particles and a corresponding surge in cosmic rays from the galaxy. They revealed that the boundary is not a smooth, perfect sphere, but a dynamic, shifting membrane buffeted by the pressures of interstellar space. While the Voyagers gave us two single points of data, the IBEX mission, the Interstellar Boundary Explorer, has given us the big picture. From its orbit around Earth, IBEX does not look at light from stars. It detects energetic neutral atoms that are created at the very edge of the heliosphere. By collecting these particles, it has painted a full sky map of our solar system's protective shield, revealing a surprising and unexpected structure. The map showed a bright, ribbon-like band of intense emission snaking across the sky, a feature that current models struggle to fully explain. This ribbon appears to be aligned with the direction of the galaxy's magnetic field, a clue that the forces shaping our cosmic bubble are not just internal, but are influenced by the vast magnetic landscape of the Milky Way itself. Understanding the heliosphere is not just an academic exercise, it is fundamental to our own story. Its stability and protective qualities were a prerequisite for life on Earth. By mapping its contours and learning its physics, we are not only defining the boundaries of our home in space, but also understanding the essential environmental conditions that allowed us to be here at all. This knowledge also paints a clearer picture of the journey any future starship would have to undertake, first leaving the protective embrace of our sun before venturing into the raw, radiating wilderness of the galaxy. The idea that we are citizens of the cosmos is more than just poetry, it is a serious scientific possibility. The theory of panspermia proposes that life itself, or at least its essential ingredients, is a traveler, hitching rides on asteroids, comets, and even our own spacecraft. This is not a new idea, but recent discoveries have given it profound new weight. We have found amino acids, the fundamental building blocks of proteins, inside ancient meteorites that have fallen to Earth. These are not just simple molecules, they are the same complex organic compounds that form the basis of all life on our planet. Think of these space rocks as unopened delivery trucks carrying the raw materials for biology across the vast interstellar distances. This concept elegantly connects so many of our discoveries. The organic molecules in the plumes of Enceladus, the boron on Mars, the tholins on Arrokoth, all of them point to a universe that is not just habitable but actively prebiotic, a vast factory producing the chemistry of life. It suggests that the spark that ignited in Earth's early oceans may not have been a singular, local event, but a seed planted by a passing comet. Even the extreme resilience of microbes, which we know can survive the vacuum of space and intense radiation aboard the International Space Station, lends credence to the idea that life could endure an interstellar journey, frozen in the icy interior of a wandering body. This shifts our perspective on contamination as well. Every probe we send to a world like Mars or Europa carries with it a cargo of terrestrial microbes. We are unintentionally already testing the panspermia hypothesis in one direction, potentially sowing earthly life on other worlds. And if it can happen by accident with our technology, why could it not have happened naturally over billions of years? The implication is staggering. Life may not have originated on Earth at all. Our entire biological history, from the first cell to the human mind, could have a cosmic origin. We may all be descendants of interstellar travelers, and the search for life elsewhere becomes a search for our own deepest, most distant relatives. Each of these 30 discoveries is a key turning a lock in a door we are only just beginning to open. From the first confirmation of a world in a habitable zone to the unsettling push of dark energy, from the hidden oceans of icy moons to the ancient whispers of asteroids, each breakthrough does far more than fill a page in a textbook. They are the engines of our future. The hunt for a second Earth drives the development of new propulsion systems. The study of black holes and gravitational waves refines our most fundamental laws of physics. The search for life in a Martian rock or a distant atmosphere forces nations to collaborate, sharing resources and intellect in a common, profound quest. These cosmic revelations are not abstract. They are the blueprints for new energy, new materials, and new medicines. They fundamentally alter our perspective, shrinking the tribalism of our world by revealing our true context, a fragile, living speck in an unimaginably vast and active cosmos. This is not a passive story for us to simply watch unfold. It is an invitation to participate. The next great discovery, the one that changes everything, is waiting. It requires your curiosity, your support for science, and your willingness to look up at the starry sky and wonder what is next. The universe is speaking. It is time for all of us to listen.